Hello and welcome to Lecture 7 in the Python programming series, and today we are going to continue our discussion about classes and review a little bit about what we did in the previous lecture, and then we're going to finish out chapters 17 and go into inheritance into chapter 18. Again, the information in last lecture, this lecture, we're going to expand a little bit more and go a little bit more into it in the next few lectures. So please just let it kind of wash over and try to understand it as much as you can. As a review, we went into object-oriented programming, and we discussed how it is a computer programming model and it is a way to do things in which you create an object rather than functions and logic. So your object will contain properties and methods that know how to work with what it has. So typically it's used for large, complex problems or programs, and we can reuse those objects over and over again. We use the example of a human, which a class could be a human. The object of that class or the instance of that class would be a specific human with a name. Each human will have things such as hair color, eye color, skin color. Here we have email and addresses, and those are the nouns associated with that class. The verbs, on the other hand, are the methods associated with the class. So here we have verify and send email, but I like to think of walk, talk, breathe, things like that. A class is nothing more than a programmer-defined data type. We will create a class object based on the class definition. When we create that new object, we are said to create an instance of a class. We went through the example of our point, and then we expanded that to be a rectangle, where a rectangle is a point or a corner with a width and height. So here, for example, just as a review, I've got my box equals a rectangle, which box.width, we use that dot notation to access the attributes within that class object. So my box.width equals 100 and my box.height equals 200. My corner is equal to an instance of the point class, and then I can stack those dot notations. So I've got my box instance dot corner attribute dot x attribute. So that is the x attribute associated with the point corner, which is associated with the rectangle box. And I've set both those x and y to 0, so my corner point is at the origin. We discussed functional programming styles, and we want to stick to writing pure functions. And remember, pure functions do not modify objects in any way. They take input and they return output. Modifiers, on the other hand, are only used if there's no other way, and modifiers will change the actual object. So we don't want to have any internal state changes that affect the objects when we're writing our typical functions. We discussed methods and how methods and functions are relatable, and that a function is associated with a particular class to do a specific activity on the class. So the method is defined within the class. So it's basically a function that belongs inside a class that belongs to that class. So only that class knows about it. The syntax for the methods and the functions are very, very similar, but they're slightly different because of the location and the indentations. Then last, we wrapped up with talking about the initialization of classes. And this is how you are to set the values of attributes within a class to an initial value based on what the user has, or just based on what the programmer wants. Again, it's common in these init classes to have parameters names the same as your attribute name. So for example, here I have hour equals 0, minute equals 0, second equals 0. My user can create an instance of a time, either sending it an hour and a minute, or an hour, minute, or second, or not sending it anything. If we don't send it anything, it is going to default to 0, 0, 0. We also discussed this self, and when we see this word self, it means the object in which it is contained. Now let's keep expanding on this idea of objects and what we can do. So we can specify the behavior we want for operators in user-defined types. So if we have a user-defined type as a capital T time, what does the plus sign do? What does a minus sign? Multiply, divide. Well, what do we want it to do for time? Typically, we would want it to add seconds, add minutes, and then add the hours. So it's not a typical plus as if we were to do an integer. We can define a method called underscore underscore add underscore underscore, and you can see a pattern happening here with these double underscores. And we can say we're going to convert that time to seconds, add to it the amount of seconds in the other time, and then return the new time based on the new amount of seconds. So here I define the add, I have self and an other, I convert everything to seconds, and then I return the seconds converted back to a time. Then I can now use a plus sign in order to call this underscore underscore add method. So on the right down here at the bottom, I have start equals a time, duration equals a time. I can say print start plus duration. That's going to call this underscore underscore add, and it's going to do what this add specifies. That's called overloading a function. In particular, we are talking about overloading operators. So when you use the plus sign operator, it's going to invoke an underscore underscore add method. When you print, it invokes an underscore underscore str method. And this has been happening all along behind the scenes when we talk about the integers, floats, strings, even the lists, tuples, and dictionaries. We can change any of these methods to define them for our user object. And here I'm going to look at this link up in the Python documents, and you'll see exactly what we mean. There's a section in the Python documentation, and it's called Special Method Names. And it is all about being able to customize different things that are built in to Python with your user-defined types. So if I scroll down, I have a few different things that you might recognize. Here I have the str, I've got some bytes, I've got some format, but here I want to draw your attention to this section right here. I've got a double underscore LT, LE, EQ, NE, GT, GE. These functions right here, or these methods, are going to be your less than or equal to, not equal to, greater than, or greater than and equal to. So if you read the paragraphs that follow below, if I were to type x less than sign y, it's actually going to call x dot underscore underscore LT underscore underscore and send it y. So if I wanted to implement for my time class, and I wanted to be able to say time 1 equal sign time 2, I can do that by overriding that EQ method. That's a good way to be able to reuse what programmers are used to using when we do some of these comparisons. There are a lot more examples through here. You can actually scroll down and look at them yourself, but it's going to give you some information about different things that are built into Python that will allow you to use what programmers already know. Let's go ahead and get back into our PowerPoint. Good programming practice is to do something called a type-based dispatch. And what that is going to do is it is going to say, based on what data type my variable is, it knows how to take care of that. So for example, I have a time here and I've overrode the _ add. The original way that I programmed this method was, I'm assuming I have 2 time objects. But what if I had a time object and I sent to it an integer? Well, it would not know how to handle that unless I tell it. So here I have 2 methods, one called add time and one called increment. Add time is going to take 2 time objects and add them together, whereas increment is going to take a time object and add an integer to it. Now, if you look at my _ add, my overriding function for the actual plus sign symbol, it says if is instance is a time, add the time, otherwise add increment. So built into that method, I can either add 2 time objects or I can add a time object with an integer. The is instance is going to return a true if the value is an instance of a particular class. So in here I said, is this an instance? Is what I sent it, other, an instance of the capital T time class? If it is, add 2 time classes together. Otherwise, I'm assuming it's going to be a number and I want to increment instead. So this is very, very good programming practice because you're not always sure how you're going to use those operators, and they can be taken in multiple different ways. So both of these ways, if I add 2 times together or add a numeric to a time, they can both now use that plus sign. So for example, here I've got a start time and I have a duration time. I can actually say start plus duration, which are of the 2 capital T time objects, and it will give you a value. Or I can say start plus the 1337, and then that will add 1,337 seconds onto my start time of 9:45 and give me an output of 10:07. Notice there was absolutely nothing done differently on my part other than using that plus sign operator. Everything is built into the class time. Now, one thing I did not take care of here is if I were to send it the numeric first and then the object, that one's not being taken care of. So if I say print 1337 plus start, which is basically the opposite of the line ahead before it, it's actually going to give me a type error. So it's going to say unsupported type. It's going to think it's going to have an instance first because up here I have self first and then other. So it's not going to recognize that at all. Now I can take care of that by something that we call right side adding. And the right side add is going to allow you to flip either side. So I can define my _ right add, RADD, with the double underscore, send it self and other, and if I did that, that is going to ensure that whatever I do, it is going to add properly with the object first and then the numeric second. So that is going to return the object dot underscore underscore add. One of the terms that is used a lot in object-oriented programming is polymorphism. When I look at the word polymorphism, the word poly means many and morphism means forms. So polymorphism is going to be having many forms. And this is the programmer writing functions and our methods that are going to work correctly for arguments of different types. I'm going to have many different forms of that add based on what data type I have. Now, the difference is we don't need the type-based dispatch in this case. Functions that are going to just be able to work with multiple types are called polymorphic. So for example, sum. Sum is going to work as long as your object has a method that allows use of the plus sign. And we've seen sum work with integers and floats, for example, and it works the same both ways. Another good example of polymorphism that we've used previously is that len for length. Now, not even looking at any type of user-defined objects, we have used len with a string and it gives me the number of characters. We have used len with a tuple and it gives the number of items. And finally, we used len with a dictionary and it's going to give us the number of key value pairs. So even though it is giving me 3 different things, right? Number of characters, number of items, number of key value pairs, I can use that len method on strings, tuples, and dictionaries, and it works very, very similar. So we can say different classes can use the same methods. So for example, here I've got a car, a boat, and a plane. And I can define a method called move in all of them because all 3 of them move. A car moves by driving, a boat moves by sailing, and a plane moves by flying. So here I've created a class car, I'm giving it a brand and a model, and I'm saying that if I tell a car to move, it's going to drive. Here I've got a class called boat. I also have a brand and a model, but if I tell my boat to move, it is going to sail. Lastly, I have a plane, which I have a brand and a model, but if I tell a plane to move, it's going to fly. So here I can say I can create a car, I can create a boat, I can create a plane, and I'm giving it brands and models such as Ford Mustang, a Biza Touring 20, and a Boeing 747. Then I can actually go through each one of them and tell it to move. So for here, I can say for X in car, boat, plane, X.move. Every single one of them has a method defined called move. So I can treat them all as if they're the same when I do something like a for loop. One of the big goals of object-oriented programming is to create maintainable software. And in order to do this, we're going to keep our interfaces separate from our implementations. And this means that your method should not depend on how the attribute is represented in order to be used. Now, finally, we're going to kind of wrap up, but it's a long wrap up, by looking at something called inheritance. And that, again, is another one of those lovely OOP buzzwords, and it's probably the one most often associated. But it is the ability to define a new class that is a modified version of an existing class. So, My question to you, what is a human? What is a child? And what is an adult? We can technically say that a child is a human, an adult is a human, right? They are a modified version of a human. A child is a tiny human. An adult is a large human. So your inheritance is going to allow your class to inherit all of the methods and attributes of another class. So for example, it's going to get everything from the class that it inherits. So the parent class is called the class being inherited from, also called my base class. And a child class is going to be the class that inherits from the other class, also called a derived class. We often have a relationship between children and parents by saying a child is a parent. That doesn't work as well, except if we go back to what we just asked about a human, a child is a human. An adult is a human. So that's different than a has a composition, but we're not going to get into that in this class. Looking specifically at your parent class, any class can be a parent class, so the syntax of a parent class is the same as everything we've been doing so far. If I go back to my car, boat, plane example, I can say that they're all going to be a vehicle. Now, I have deviated a little bit from the book when talking about inheritance because my favorite example is using this vehicle example. There is another example in the book using cards and decks and hands of cards. Feel free, go ahead, read through that, but I think it makes more sense using the vehicle example. The parent class is going to have in it everything that is similar to the children. So here I've got my class. I used brand and model for all three of them, and I did use the move. So in this one I say a vehicle just moves. I don't give any kind of indication as to how it moves. Now a child class, on the other hand, a parent class is sent the parameters when creating the child class, and then that's going to allow that child to inherit everything that the parent has, both attributes and methods. So for example, here I've got a class car, and I'm just saying it's just a vehicle, it just moves. So it's going to inherit everything the same that the vehicle has. Now I can create a boat and a plane where I define that move class to do something different than what the parent said. So in this case, I've said a boat is going to sail and a plane is going to fly. Those child classes are going to do whatever it overwrites first. And then if it doesn't have anything overwritten, it is going to default back to what the parent says. So let's put everything together. I've got my class vehicle at the top, and then I've got a car, boat, and plane, which are each a type of vehicle. Car is empty, so it's just going to inherit the brand, model, and move from the vehicle. But boat and plane is going to inherit brand and model because I didn't say anything different, but it is going to do something different when I say to move. So for example, here I've got my car, boat, and plane. They're exactly like I did them before, but now I can print the brand, the model, and I can tell it to move. So if I were to do that for the car, it's going to print Ford Mustang and it's going to say move. If I do it for the boat, it's going to say Ibiza Touring 20 and then it's going to say sail. If I do it for the plane, it is going to say Boeing 747 and it's going to say fly. So it's going to look within itself first, and if it does not have that thing, then it's going to go back to its parent. So here I tell it to move. It does have a move, so it says fly, but it's talking about a brand and model. This class plane doesn't have it, so I look at vehicle. Vehicle does, so that's where I go back to. Now, I've got this vehicle object, and I can create an instance of it. So what attribute does this vehicle have? Well, it has a brand and a model, and it will associate that brand and model with every class object that is a vehicle, every parent that's a vehicle, and every child that uses vehicle as well. Now, instance variables are variables that you can define within your child or associated with the instance of that class. Every vehicle here has its own brand and model, but we could add different attributes to a boat if we would like to, or a car. So for example, if we want to say number of wheels, we could put that on a car. A boat necessarily wouldn't have wheels, so we would put it in the car class and not necessarily the vehicle. Here is a graphical representation of the inheritance classes. So here I've got my class at the top that is a vehicle. In my vehicle, I've created a car, a boat, and a plane, and I can actually extend this as many times as I want. So for a car, I've got electric, gas, and hybrid. Plane, I've got military and civilian. I could even break that down even more if I wanted to. So for car, gas, I can say race car, street car. I can pull this out as far as I want. Now, inheritance, you can modify the version of the existing class. So what operations do we need for a plane that we wouldn't necessarily need for a car? Fly, wings, like how does it fly? How many wings does it have? How long are the wings? Does it have a propeller? These are things that we could add to plane that would separate a plane from a car, but we don't want it in vehicle because not every vehicle has these type of operations. This is called a simple inheritance because your plane and your vehicle have a parent-child relationship. Now, if I were to look at the next level down, so the modified version of a car class, what operations do we need for a race car that we wouldn't need for a passenger car? I don't know, does it have nitro? Does it have sponsors? What's the horsepower? Things like that. These we could put into the race car version and not necessarily a passenger car version, but they're both a type of car, which is a type of vehicle. This is called a multi-level inheritance. So you've got different levels inheriting from each other. So even though a race car might be down here as a car, it's still going to have a brand and model that it gets from way up here in vehicle. Because everything the race car has, it has everything a car has, which has everything a vehicle has. Lastly, class diagrams. Typically, we have looked at so far stack and object diagrams. And these types of diagrams are going to show a snapshot of time. So it's going to show the current state or the current values of attributes within the object. Now we can add to it a class diagram, and it is going to be an abstract representation of the structure, very similar to what we just saw. But it's going to reference objects in other classes, it's going to reference the inheritance, and it's going to reference the dependence. Now, I was not able to find a class diagram that I liked that had my vehicles, so I found this one that has people, students, professors, and courses. Here you can see that a student and a professor are people, and students and professors have classes. So an arrow with a hollow triangle such as this is a relationship. A student is a person. A professor is a person. A regular arrow, if we were to have that, it means has a relationship. Here we've also got the little asterisk or the star, and that means that it has a number of. A student has many classes. A professor has many courses, and a course has many students. If we were to have something that looked like a dashed arrow, that is what we call a dependency, and it would be dependent upon something else. If you need a little bit more reading on inheritance, here are two good resources that have some of the examples similar to what I did in this lecture. So take a minute, look at those links, and you can get a little bit more information reading on inheritance other than what we have in our book. I'm going to go ahead and also link these in this week's resources. So this lecture put a lot more information building on those classes that we talked about last time, but we did a quick review of our last lecture with classes and the instances and methods and functions and stuff like the attributes. Then we expanded a little bit more on those methods where we finished last time, and we started into our discussion of inheritance. Again, we're going to be looking and revisiting the ideas of all of this in our next upcoming lecture or two. So hopefully this makes sense. If not, let me know, and I will see you in the next lecture.